Hello, everybody, and thank you for joining this webinar on direct air capture and ocean storage by Puro.earth. We will get started in a few minutes. Let's give a minute or two for people to join the webinar. And while we are waiting for more to join, please locate your Q&A button on my screen. It's at the bottom of the Zoom window with a question mark in it. And you can write your questions there during and after the presentation. So welcome everybody to this webinar on direct air capture and ocean storage by Puro.earth. I am still waiting for people to join and just mentioned that Q&A button should be used for questions, and you can already write questions during the presentations. All right. Very good. My name is Marianne Tikkanen. I am the co-founder of Puro.earth and head of Standard, and I am thrilled to be here today to introduce a new ocean-based durable removal methodology which has reached the milestone of public consultation. I will be hosting this webinar together with my colleague, Dr. Richard Hans.
Hello everyone, I'm Richard Hutz. I'm the head of science here at Puro.earth. I have a long background as a scientific researcher. My area of specialty is chemistry. I've been here with Puro for about 2.5 years.
Together we will give you a brief intro first to Puro.earth for those who don't know us, then a 15-20 minute presentation of the webinar that we are asking the consultation on, and then in the end we will leave 10-15 minutes for your questions that would be addressed. So please put your questions to the Q&A. So let's look at Puro.earth before deep diving to the methodology at hand. So Puro.earth is a global carbon crediting standard and registry for durable carbon removals. Our standard covers these carbon removal methodologies, and all of these methods ensure that the CO2 is removed and durably stored for long term over hundreds or thousands of years. The lower row removal methods have been there for a while. Biochar, carbonated materials, enhanced rock weathering, terrestrial storage of biomass, and geologically stored carbon, which covers both BECCS and DACOS. The top row is now what we have introduced in the past weeks, the ocean methodologies, direct air capture and ocean storage, which we are discussing today, and ocean storage of biomass, which is actually the final date for public consultation comments for that methodology is today. So if you're interested in that one, please give your comments today. And methodologies are of course the most visible part of Puro.earth, the rules that the scientists write, but there is more. We also orchestrate the certification and verification by third-party auditors, and the Puro registry is where the life cycle of the issued removal credits, the CORCs, is tracked from issuance to retirement. Puro.earth started first commercial operations in 2019, and since then we have issued removal credits globally in all continents actually, Americas, Europe, Asia, Australia, and also Africa. And I am very excited that we are now introducing our second ocean methodology, direct air capture and ocean storage. And I'd now like to hand over to Richard. And remember that already during his presentation, you can write your questions in the Q&A box and we'll get them addressed. Over to you.
All right, thank you, Marianne, for the introduction. So let's take a brief look at the most important aspects of the direct air capture and ocean storage methodology, or DACOS for short, and afterwards we'll answer some questions about the methodology. So to begin with, there are many ways to classify carbon removal methods, but in essence, carbon can be sequestered through either physical or chemical barriers. For example, in the geological storage of carbon, that's an example of a physical storage if you store CO2 under a caprock. But here we actually focus on the chemical storage of carbon in the ocean, where CO2 from the atmosphere is turned into stable carbon-containing species, which ensure the long-term storage of carbon. So let's take a closer look at the process of this DACOS methodology. It is conceptually very simple, and it can be divided into 4 main stages. So in the first stage, you take seawater into a land-based reactor. In that reactor, we utilize electricity to change the pH of the water and split it into an acidic and alkaline stream. So this process is called electrolysis. In the second step, we push air to flow through the alkaline water stream to take up additional CO2 from the ambient air, and it is stored in dissolved and solid forms in the alkaline water stream. Thirdly, we neutralize and re-equilibrate the acidic water stream using alkaline rocks. And finally, the re-equilibrated seawater, together with the stored dissolved carbon and solid carbon, is then discharged back into the ocean. Additionally, solid carbonate minerals can be separated from the water and stored on land. Now, let's take a closer look at the actual process. So on the right-hand side here, you can see a flow chart of the process indicating the steps from the last slide. The process itself is a rather straightforward electrolysis of seawater, and the main inputs to the process are naturally seawater and electricity, but also atmospheric CO2 and alkaline rocks, while the outputs are seawater enriched with dissolved carbonate and bicarbonate ions, so the dissolved carbon, and the carbonate mineral solids. Additionally, the process produces hydrogen and also some oxygen. Now, in this methodology, carbon is stored in 2 forms, as dissolved species, that is mainly bicarbonate ions, and as solid carbonate minerals, for example, solid calcium carbonate. The dissolved species are stored in the ocean, while the solid minerals are mainly stored on land, although some particulate solids can also be stored in the ocean. Now, it's scientifically very well known that both of these forms of carbon, the dissolved and solid, are very durable, of the order of at least 10,000 years or more. So, in fact, both solid carbonate minerals and in particular the ocean naturally hold and store vast quantities of carbon. So here I have exemplified these with 2 quotes, one from the National Oceanic and Atmospheric Administration, or NOAA, which is a US scientific and regulatory agency, and another from the IPCC, attesting that both of these forms of carbon removal are indeed extremely durable. So in other words, there is extensive scientific evidence to show that this form of carbon removal is basically for all intents and purposes permanent. Now, besides the high durability of carbon storage, we must also ensure that the methodology is safe to operate. Or in other words, we must make sure that the risk of, for example, environmental impacts are properly assessed, monitored, minimized, and reported. Now, fortunately, in this case, the closed system nature of this removal method works in our advantage, as the process can be very easily and continuously monitored, including comprehensive measurements of water quality and other key indicators. So focus on safety is, of course, a key component of all Puro standard methodologies, and we have taken great care to ensure that this methodology is no exception. The eligibility criteria in the methodology themselves are designed to minimize any risks, and the methodology additionally includes further requirements for the comprehensive assessment of of risks tied to monitoring, mitigation, and reporting requirements to ensure that the projects actually result in no harm to the environment or any of the surrounding local communities. Now, we have seen how this methodology ensures the safety of operations and the durability of carbon storage. But there's, of course, another foundational pillar of no less importance, and that is robust quantification of carbon and carbon accounting. So this methodology includes very detailed requirements and calculations of all aspects relevant to the quantification of carbon stored. But the basic principle shown here is very simple. Here in this equation is shown the Cork-Master equation, which basically boils down to the simple concept of net carbon removals equals carbon stored minus carbon emitted. Now here below, the waterfall graph shows an example of this concept. We start by quantifying the gross amount of carbon stored, from which we deduct any direct or indirect process emissions, as well as any carbon losses, and additionally any baseline removal, that is any carbon that would have been naturally stored without the project activities. Now let's take a closer look at a few of the terms in more detail. Firstly, let's focus on the C stored, that is the gross amount of carbon stored. So simply put, the gross amount of carbon stored can be rather straightforwardly quantified by measurements inside the closed system processing facility. Essentially, we do this by monitoring parameters such as water flow rates and chemical composition of the ingoing and outgoing seawater. These measurements are commonplace in chemical process monitoring, and they utilize rather standard equipment such as flow meters, chemical sensors, weighing equipment, and so on. Now, another term of great importance are, of course, the project emissions. This term represents all the different sources of GHG emissions directly attributable to the project. And here we have divided that term into two basic components. The operational emissions, which signify basically the energy and material inputs used to operate any infrastructure and machinery. And on the other hand, embodied emissions, which refer to the emissions associated with construction of facilities themselves. For example, operational emissions would include electricity needed to run the facility at the electrolyzer, as well as emissions related to sourcing alkaline rock and transportation of it. And on the other hand, embodied emissions would include, for example, the construction of the facility itself, including things such as production and transport of construction materials, energy used during construction works, and disposal of the wastes. Now, we talked about basically three pillars of safety, durability, and robust accounting. And we've seen how they work, but let's take a closer look at how the methodology actually ensures that these principles are fulfilled, evidenced, and verified. So this is where the monitoring, measuring, and reporting requirements are paramount, and the methodology includes indeed comprehensive requirements on all of these aspects. For example, the methodology requires monitoring of things such as eligibility compliance, so net carbon removal quantification, or environmental and social impacts. And the fulfillment of these requirements must then in turn be shown by robust, verifiable, and auditable measurements and data collection. And finally, the projects must collect and present this evidence of project performance for verification by a third-party auditor. Now, here I have briefly discussed the main key elements of this methodology, but let me recap the key takeaways of this methodology. So here in the left-hand side, you can see the system boundary of the DACOS activity, and on the right-hand side here, the key aspects. So this methodology is focused on electrolysis of seawater in a closed system reactor under controlled conditions. We capture atmospheric CO2 and store it as solid and dissolved carbon species. This methodology ensures the safe and durable carbon removal over very long geologic time spans, and it includes strict requirements for monitoring, environmental and social safeguards, as well as carbon accounting. So here, as a final summary of this methodology, I'd like to leave you with this figure, which kind of exemplifies the three key elements that make this methodology safe, durable, and robustly quantifiable. Here, the closed system process ensures the robust monitoring and the environmental impacts, and that the environmental impacts and risks are controlled and contained and minimized. Finally, the re-equilibration of seawater in the processing facility before discharge ensures that the durable storage of carbon in the ocean without disturbing any of the natural processes. Right, handing back to you, Marianne.
Yes, thank you, Richard, for a walkthrough of the key parts of the methodology. This methodology development work was initiated by Aquatic. We like to thank very warmly for your collaboration. And this is now open for public consultation until February 21st. So this is a chance for any of you to give your input and improve the rules that we are drafting and proposing. And we will address your comments and supporting or criticizing feedback. So please do download the methodology. It's quite long. You can read it top to bottom, or then you can find the interesting sections for you to address on and give us feedback in the feedback form. And then this will be improved and go to final approval. So thank you very much for listening so far, and then let's move to the questions and answers. Let me see if we have questions here. Yes, and you can still put your questions to the Q&A menu in your Zoom window. So let's see here. There may be some questions that are overlapping, so I may be rephrasing these and combining these. Here is an interesting question, wondering about the naming conventions. Let's start with this, Richard. The question is that why did you choose the name direct air capture when it is not DAC direct air capture as I understand it?
Okay, yeah.
You can stop sharing.
Stop sharing here. Okay, great. Thank you, Marianne. So that's a good question. So, I mean, it's always tricky when we decide a good name for a methodology. I mean, there are so many different kind of aspects which you could use in the naming. You could name it after, say, the storage process, after the capturing process. There are many different options here. I mean, it's true that there's no separate DAC unit like there is, for example, in DACS or something, but this is really direct air capture if you think about it sort of closely. So in this case, the alkaline water stream captures CO2 directly from the ambient atmosphere, and it kind of acts like similar to a sorbent would in DACS. So there is no like intermediate processing step to capture the CO2. So, for example, if we compare this to, say, enhanced rock weathering, in that case, CO2 from the atmosphere is first dissolved in seawater, and that seawater would react with kind of alkaline rocks. But here, rainwater. Yeah, the rainwater the CO2 in the rainwater would react with the alkaline rocks. But here there is no such intermediate step. But the CO2 is captured directly from the atmosphere, and that's kind of why we chose this name.
Thank you, Richard. Here is another question to you. Very many inputs and outputs. Are you sure all inputs are included in emission accounting? For example, the alkaline rock production for it.
Yeah, so it is true that this methodology includes quite a bit of various inputs and outputs, and I can say that we have taken great care to include them all in a sort of comprehensive and robust fashion. So in the methodology, the LCA requirements and the quantification of process emissions are elaborated in great detail in section 5. And so in this methodology, the bulk of the emissions are related to electricity use by the electrolyzer. So that's already like a huge chunk, or a big chunk of the emissions are basically just from that. But the methodology includes quantification of all relevant emission sources, and in the case of alkaline rock that was asked, it is necessary to include, for example, emissions from sourcing the rock. If there is need for, say, additional grinding of rock, then emissions related to that, emissions from transporting the rock from its source to the DACOS facility, and like basically all steps in the system boundary are taken into account in the methodology.
Thank you, Richard. Here is a generic question. I can answer this myself. The question is that now that the methodology is there, what does a project have to do to get the credits? So the projects in this methodology have to take the same steps that any methodology or any project in any methodology in Puro standard. So first they have to register their company and their project in Puro registry. Then they have to follow the rules in this methodology about reporting and providing the evidence. That evidence will then be captured in the digital platform and delivered to the verifier, the independent third-party verifier, who then verifies, and if they are found to be meeting all the rules, then the verified number of net removal is issued to them as credits in their registry account, and then they are free to move those, transact those credits, trade them, and deliver them where they like and as they like. And just a note, the person asked now that the methodology is ready. It's technically not quite ready yet. We are still in public consultation phase, very much relying on your inputs to make the final tweaks, and then it will go to the final approval in the Puro Scientific Advisory Board, chaired by Professor Miles Allen. Let's see, there are quite many questions about environmental risks, Richard. If we take these together, so what environmental risks have you identified, and how do you make sure that projects do not impact marine life negatively?
All right, yeah, so that's an excellent question. So we do take any potential for negative environmental or social impacts very, very seriously. And in this methodology, first of all, there is a requirement for all project proponents to identify risks to, and those requirements are then tied to monitoring requirements and reporting requirements. There's need to follow local regulatory thresholds and things, but especially, for example, one key risks that we have identified that the project need to take into account are indeed basically changes to local ocean water chemistry. So in the case of this methodology, these risks are sort of mitigated and taken into account by sort of several different means. So first of all, there are no sort of significant changes to ocean chemistry because of the nature of the process, where the seawater is re-equilibrated inside the closed reactor system, so that we can ensure that the water chemistry of the outflowing water matches that to the ingoing water, and there are no changes to the local biosphere. Secondly, it's simple to monitor the process, and for example, you can quite easily sort of stop operations if something is detected, and this sort of this closed system nature of the process really helps to mitigate and contain any possible sort of environmental risk or changes to the water chemistry.
Yeah, let's continue there. There are a couple of people asking about the ocean alkalinity and how is this different from ocean alkalinity enhancement, and can ocean alkalinity enhancement projects use this methodology?
Yeah, so the short answer is no. Ocean alkalinity enhancement projects do not fit under this methodology. So the simple reason for that is, first of all, that the methodology outlines eligibility criteria in such a way that you must use electrolysis process in a sort of closed system reactor, so that rules out OAE. But the sort of conceptual reason for that is that this methodology is quite different to OAE in several key respects. So, for example, the speed of the reaction, the measurability, the containment of environmental impact. So, because this process operates in a closed system reactor, it can be monitored and measured very easily, and the carbon removal can be quantified simply through measurements. And this also means that the speed of the carbon removal is very different. So in this case, when the seawater leaves the reactor, carbon removal has already happened. While in ocean alkalinity enhancement, especially in the open ocean, there's a significant delay between adding alkalinity to the water and uptake of CO2 into the ocean. So this, like air-sea gas equilibration, can take, say, of the order of a year or longer to occur, depending on sort of specific conditions. And furthermore, the sort of containment of potential environmental impacts and the risk associated are different. So in this case, we can monitor the process very simply in the reactor, and if need be, the process can be halted. Whereas in open ocean alkalinity enhancement, you cannot really, once you release the alkaline feedstock into the water, there's no taking it out. So the potential for environmental impact is much greater, and the risk profile is different. So for these reasons, we have made the sort of conscious decision not to include ocean alkalinity enhancement methods under this methodology.
Thank you, Richard. To a non-chemist sounds like alkalinity is alkalinity, but there seems to be very big differences. There is a question about where can these projects operate? Can projects operate in international waters?
Okay, I don't see that as logistically possible. I mean, this methodology really requires a sort of land-based treatment facility in like on the shore. I guess one might sort of envision a mobile platform of some kind, but that's not really possible or feasible. In my opinion, so the short answer is no. But also, on the other hand, this methodology does require local permits for operation, and it is tied to sort of local regulatory frameworks and limits. So also from a kind of like regulatory standpoint, you cannot operate sort of rogue in international waters away from any regulation.
Okay, and this word re-equilibrate seems to be very puzzling. I don't understand what re-equilibrate means. Can you explain it?
Yeah, so re-equilibration of seawater is indeed a key concept here in this methodology. So it basically means to change the composition of seawater back to what it was. So in this context, when we pump seawater into the reactor and run the reaction, we change the chemistry of the seawater. For example, we change its pH. From regular seawater, we get an alkaline stream with increased pH and an acidic stream with lower pH. So it's very important that we then at the end of the processing in the facility, change the chemical composition of the water back to what it was, to avoid, for example, degassing of the CO2 that we have just captured. For example, if we were to just release the acidic water stream back to the ocean without doing anything to it, it would cause degassing of CO2 from the ocean, not to mention significant environmental impacts. So re-equilibration here means that we, for example, realkalinize the acidic stream and change its composition back to the original composition of the seawater, or very close to it, so that there are no these kinds of negative effects.
Thank you. There is one question addressed to Aquatic. If Aquatic can come on camera, I can take one question in between, and then if you like, you can answer that one. So there is a question that I can answer. This is not chemistry. It is about allocation of emissions. So the question is, where there are two co-products, hydrogen and CDR, so the carbon removal, how are the emissions allocated between these two? Very good question. That is a typical situation with multi-product, co-product processes. And we require the projects to follow the rules from ISO standard, ISO 14044, for life cycle assessment rules and allocations. And where there are multiple co-products, basis for allocation of emissions is typically based on a physical relationship, for example, energy content. Here that is not possible because carbon removal does not have energy content. Hydrogen has, but that is not the common denominator. So then we fall back to other options available in that ISO standard. And here we require the projects to use the economic value and use the allocation between these two co-products based on that. The details are described in, I believe it was section 5, where these project emissions are detailed in, and you are kindly asked to read those and give your input and comments if there is something that you think should be done differently. But then I see that Edward Sanders is there from Aquatic. Thank you for joining, Edward. And if I read the question to you, Aquatic's process is also producing hydrogen. Why do you need carbon credits? Are you even additional, is the question. Over to you, Edward.
Well, hello, and thank you very much for that question. Indeed, hydrogen, yes, it is a valuable commodity, and a combination of green hydrogen and carbon credits can significantly improve the financial viability of what we are doing. About 30 kilograms of hydrogen is produced for every 1 ton of carbon that would be removed under this protocol. This is a good thing. So the co-production of hydrogen lowers the production cost of high integrity credits, and that's important to drive greater demand for CDR. The hydrogen could be used within a fuel cell entirely inside the boundary to lower the energy content. Alternatively, if it is sold, monetized, any revenue from the hydrogen mustn't be the sole reason for the project. And the Puro methodology assesses this and validates that indeed it isn't, and those carbon credits, when produced, are additional.
Thank you, Edward. And now that I have you there, is there anything else you'd like to add or complement to the discussion and presentation that we have had here?
I think it'd be really helpful to see as many comments as we can have back. It's a very comprehensive protocol, and we are trying to bring to the market high integrity credits, and that will come from having the transparency and the public feedback. So please, I invite you all to get your comments in.
Thank you, Edward. Let's start to wrap up. As a final question, let's take this one here. Are there other projects than Aquatic that can use this methodology? What do you say, Richard?
Yeah, so while this methodology was initiated by Aquatic, and we have been working with the Aquatic team in close collaboration on this methodology, it is in no way limited to only Aquatic. So all projects that meet the eligibility criteria can indeed use this project and get credits from it. Now, I see that in my opinion, there's great potential to this methodology, and it presents sort of like an interesting opportunity to both projects but also buyers. And the way this kind of works is that we as a standard are an enabler of sorts. So we've seen this with other projects as well, that when we publish a methodology, it sparks interest, and more and more projects then come to our ecosystem and start to use the methodology to generate carbon removals. And I believe and hope that this is the case also with this methodology. So the short answer is yes, and I welcome any interested projects to join us in generating durable carbon removals with the DACOS methodology.
Thank you, Richard. And then let's wrap up. Can you share the last slide again to remind people that your feedback is needed? We like to hear from you, of course, critical comments, but supporting comments as well. Open until February 21st. And please download the methodology, use the feedback form, and give your inputs here. So very exciting times. We've seen growth in other methodologies from 1,000 to tens of thousands to hundreds of thousands of credits per unit or per facility. And this methodology has that potential. So let's make it very good through consultation, and then more climate change mitigation happen also in the ocean. Thank you for joining this webinar today.
Thank you.